All right, today we're cracking open a cosmic cold case. And our suspect? It's not just some random object in the sky, it's actually famous. This is one of only 14 pulsars that we used as a cosmic landmark on the golden records sent out with the Voyager probes. You know, the map that's supposed to lead aliens to Earth? Well, it turns out this particular landmark, Pulsar B1451-68, has been sending out some seriously strange signals that have had astronomers stumped for years. So let's dive in and see if we can solve this thing.
So first thing you need to know about our suspect is that it's ancient. We're talking 42 million years old. That's an almost unimaginable amount of time for this thing to be spinning and beaming out signals across the galaxy. This isn't some new mystery. We're trying to decode a message that's been on its way for eons.
And it's not exactly next door either. B1451-68 is about 1,500 light-years away from us, hiding out in the constellation Circinus. I mean, at that kind of distance, its signals are unbelievably faint. Trying to pick them up and make sense of them is like trying to hear someone whisper from the other side of the planet. It's a huge challenge.
So what even is a pulsar? Well, imagine a star way, way bigger than our sun dies and collapses in on itself. It becomes so incredibly dense that just a single teaspoon of its material would weigh billions of tons here on Earth. As this little remnant spins, sometimes hundreds of times a second, it shoots out beams of radiation from its poles. And if one of those beams happens to sweep past Earth, blink, we see a pulse. The best way to think of it is like a cosmic lighthouse, and B1451-68 is one of the oldest, weirdest ones we've ever found.
And that right there is the heart of the mystery. We see the pulses from this lighthouse. We know it's there, but the signal isn't clean. It's faint. It's really complex, and it just behaves in this totally bizarre way. It's like the lighthouse is sending us a message, but it's in a code we just can't seem to break. So the big question for years has been, what is this thing trying to tell us?
To crack this case, scientists knew they had to attack it from all angles. The first move? Look for clues in a totally different kind of light. And that brings us to our very first piece of evidence, a faint footprint left behind in the X-ray spectrum. So, you know what they did? They brought in the big guns. They pointed one of our most powerful tools, the Chandra X-ray Observatory, right at the pulsar's last known location. The mission was pretty straightforward. See if this old, faint object is kicking off any X-rays, because if it is, that high-energy light could hold the key. But of course, there was a problem right out of the gate. It's like a crime scene with too many footprints. The pulsar had a super close neighbor, another star. So the question was, are the X-rays coming from our pulsar, or is this other star just contaminating the evidence? Well, after some really careful work, they found the X-ray source lined up almost perfectly with the pulsar, and figured the other star was contributing, at most, less than 7% of the signal. Okay, they had their suspect cornered.
Now that they were pretty sure the X-rays were coming from the pulsar itself, they could do the really cool part, analyze its spectral footprint. See, every light source has a unique signature, a spectrum that tells you all about its temperature, what it's made of, basically the physics of what's going on. This footprint was our first real clue into what makes this pulsar tick.
And wow, this is what they found. The X-ray signal wasn't just one thing. It was actually made of two totally different parts. About 40% of it came from what you'd call a thermal source, a tiny, ridiculously hot spot right on the pulsar surface. But the other 60%, that was non-thermal, created by super high-energy particles getting whipped around in the pulsar's gigantic magnetic field, its magnetosphere. So our lighthouse has this super hot bulb, but it's also surrounded by this powerful, glowing magnetic bubble. Okay, the X-ray data was a huge step forward. But the biggest puzzle, the real head-scratcher, was still lurking in the signal that pulsars are most famous for, their radio waves. This brings us to clue number 2, what I like to call the flipping code.
Okay, this is where it gets really, really weird. Light waves can wiggle or oscillate in different directions. That's called polarization. Now, this pulsar signal wasn't just one simple polarized beam. Nope, it was split into two separate modes, perpendicular to each other. And what's even crazier is that the signal would just randomly flip back and forth between these two modes. For the astronomers trying to make a map of this beam, it was a nightmare. It just created two confusing, overlapping trails in all their data. I have to tell you, this is not how pulsars are supposed to behave. It's like trying to listen to someone who keeps randomly switching languages in the middle of a sentence. Why was it flipping? Why did it seem to have two different personalities? It was like a code that was actively trying to confuse us, and for a long time, nobody had an answer.
This deep, deep puzzle forced astronomers to completely rethink how pulsar signals might even work.
And that brings us right to the climax of our investigation, the moment a brand new theory came along and finally cracked the code.
A research paper looking at this very pulsar dropped this bombshell of an idea. The theory was that these different parts of the signal, the flipping modes, the two separate tracks in the data, were, quote, the illusion of components as separate entities. What if everyone had it wrong? What if they weren't seeing two different signals, but one really complex signal that was just playing a trick on them? Now, the key to this whole thing is a concept you've seen a million times: wave interference. Just picture dropping two stones into a still pond. The ripples spread out, and they start to interact, right? Where two peaks meet, you get a bigger wave. But where a peak meets a trough, poof, they cancel each other out. That beautiful, complex pattern of bigger and smaller waves, that's an interference pattern. So here's the breakthrough. What if that lighthouse beam isn't just one simple single beam of light? What if the pulsar is actually sending out multiple waves all at once? As these waves travel across 1,500 light-years of space, they interfere with each other, just like those ripples in the pond. And suddenly, the whole mystery just clicks into place. What astronomers were seeing as two separate flipping modes was never real. It was an illusion. Just the peaks and troughs of one single incredibly complex interference pattern finally reaching our telescopes.
You know, this idea does so much more than just solve one weird case. It actually forces us to stop and question what we think we know about these incredible cosmic lighthouses and the very light they send our way.
And just like that, the case is closed. That bizarre, flipping signal from a 42-million-year-old cosmic landmark wasn't some kind of elaborate encoded message after all. In the end, it was a beautiful, magnificent trick of the light, an illusion created by the fundamental way waves work.
So let's just recap the big takeaways here. First, a pulsar's beam isn't always a simple lighthouse sweep. It can be a complex interference pattern. This means that these components and modes that scientists have been measuring for decades, well, they might not be real physical things at all. They could just be illusions. And that right there challenges some of our most basic ideas about how pulsars even work.
And that's why this whole case matters so much. Cracking the code of one single pulsar, thousands of light years away, has huge implications. It's this incredible reminder that the universe can be way more subtle and complex than it looks. Things that we see as separate and distinct might actually just be the result of a deeper, hidden reality that's playing out right in front of our eyes.
Which leaves us with this final, kind of mind-bending question. If the steady sweep of a cosmic lighthouse, one of the landmarks we put on our map for aliens, can be an illusion, a simple trick of interfering light, what else are we looking at out there in the cosmos that we might be completely misinterpreting? What other illusions are waiting for us to see them for what they really are?